Welcome to The Explainer. Today, we're diving into the pretty fascinating world of coordinate bonding. We spend a ton of time learning the standard rules of chemistry, right? But what happens when atoms break the rules of fair sharing? Well, we're going to look at the spectacular molecular rescue missions that happen when one atom steps up to literally save another.
So, here's the central conflict. We're taught from day one that a normal covalent bond is an equal partnership. You bring an electron, I bring an electron, and we share. A perfect 50-50 split. But what happens when an atom is left entirely empty-handed? What happens when it has absolutely nothing to trade, but it still desperately needs to become stable?
Let's start with Section 1, the rules of fair sharing.
Think of a typical covalent bond kind of like a potluck dinner where everyone brings an equal dish to the table. If two chlorine atoms get together, they each bring one unpaired electron, forming a single bond of two shared electrons. Oxygen atoms, they each bring two, sharing 4 electrons to make a double bond. And nitrogen atoms go all out, bringing 3 electrons each to share a total of 6, creating an incredibly strong triple bond. It's perfectly symmetrical, and it's perfectly fair.
Moving to Section 2, when atoms lack electrons.
Okay, so the absolutely crucial point here is understanding the concept of an electron-deficient atom. This is an atom that just has an unfilled outer orbital. Basically, it has empty space in its valence shell, but lacks the electrons needed to actually complete it. A classic example is the hydrogen ion, or a proton, which has a positive charge and absolutely 0 electrons. It has the empty space for 2 electrons, but nothing at all to offer in a 50-50 trade. So how does an atom like this ever find stability?
Which brings us to Section 3, Dative bonds to the rescue.
Enter the dative covalent bond, also known as a coordinate bond. This happens when both electrons in a shared pair come from the same atom. It's not a potluck anymore. One atom, which happens to have a non-bonding pair of electrons, we call that a lone pair, decides to basically treat the electron-deficient atom to a free meal. It donates both of its electrons to form the bond.
Check out ammonia here. That central nitrogen atom has a lone pair of electrons just sitting there doing nothing. And right near it, we've got our electron-deficient hydrogen ion with that empty space. Notice that exact moment of the rescue. Nitrogen donates its lone pair straight to the empty hydrogen ion. And that one act of chemical charity forms a completely new structure, the positively charged ammonium ion.
Now, here is a massive takeaway. Truly, keep this in mind. Once the dative covalent bond is formed, it's no different from any other covalent bond. Even though nitrogen provided all the resources for that new bond with hydrogen, once it's locked in, you literally cannot tell the difference between the dative bond and the other 3 normal ones. The positive charge of the hydrogen ion distributes completely evenly over the whole molecule, and the resulting shape is perfectly symmetrical.
Let's see how this plays out in a really fascinating everyday example, carbon monoxide. So, step 1. Carbon has 4 valence electrons and oxygen has 6. They share 2 pairs to form a standard double bond. But wait, look at step 2. Carbon only has 6 valence electrons in total now. It's still electron deficient. It hasn't reached its octet yet. So in step 3, oxygen swoops in. It takes one of its own lone pairs and shifts it into a dative bond between them. At the end of the day, we get a triple bond where 2 bonds are standard and 1 is dative, leaving both atoms perfectly happy with full outer shells.
Let's look at another one, Section 4, the aluminum chloride dimer.
This one is wild because it literally changes based on temperature. At high temperatures, aluminum chloride exists as a monomer, AlCl3, but the central aluminum atom only has 6 outer electrons, so it's electron deficient. As the temperature lowers, 2 of these AlCl3 molecules bump into each other and, well, they strike a deal. One chlorine atom from the first molecule donates a lone pair to the aluminum of the second molecule. And simultaneously, a chlorine from the second molecule does the exact same thing for the first aluminum. They link up into a dimer, Al2Cl6, held together securely by 2 coordinate bonds.
Just a quick, absolutely crucial reminder on how we map this out visually. Whenever you're looking at chemical structures, look for the arrow. While normal bonds are drawn as just straight lines, coordinate bonds are clearly represented by an arrow. And that arrow always points away from the generous donor atom and directly toward the electron-deficient atom receiving the pair.
Section 5, expanding to metal complexes. So let's scale this up. A complex is formed when you have a central metal atom or ion acting as a sort of central hub, completely surrounded by molecules or ions called ligands. Transition metals are incredibly good at this. They invite these ligands in, and every single ligand donates a lone pair of electrons to form a dative covalent bond right with that central metal hub.
Let's walk through this table, because the type of ligand dictates the entire architecture of the complex. Small, neutral ligands like water and ammonia can pack in really tightly. Up to 6 of them can fit around a central metal ion like copper or cobalt, forming 6 dative bonds in this beautiful octahedral shape. Hydroxide ions are also pretty small, forming octahedral shapes too, but they carry a -1 charge. But then, look at chloride down there. Chloride ions are much larger. Because of their sheer size, only 4 can physically fit around the central metal, resulting in 4 dative bonds and a tetrahedral shape.
So, what about the math? How do we calculate the charge of these massive complexes? Honestly, it's just simple addition. You take the charge of the central metal ion and add the charges of all those incoming ligands. For instance, if you have a cobalt ion with a +2 charge, bonding with 2 negative hydroxide ligands and 4 neutral water ligands, well, +2 minus 2 equals 0. The entire complex perfectly balances out to an overall charge of 0.
We've gone from simple single-atom shortages to massive transition metal architectures, all built completely on the back of dative covalent bonding. So I want to leave you with this final thought. If an atom's stability relies on the charity of another atom's electrons, just how far can these coordinate networks stretch in the materials all around us? The screen you're looking at, the blood pumping in your veins, the vivid colors and paints, they're all held together by the invisible arrows of coordinate bonds. Keep an eye out for those lone pairs, and thank you for